This presentation is part of the TI in Focus AP Calculus video series. In this video, I'll discuss some technology solutions and problem extensions for the 2017 AP Calculus exam, free response question AB1 BC1. My name is Steve Kokoska, and I'm a professor at Bloomsburg University in Pennsylvania, and I'm a former AP Calculus chief reader. Here's an outline of the information presented in this video. I'll start by reviewing the free response question, and then the scoring guidelines used at the AP Calculus reading. And I'll focus on the solutions presented in these guidelines, not how the points were awarded. Now, this is a free response question that was calculator active, and so I'll show you how to use technology where appropriate here. And because the free response questions are usually very comprehensive, I'll suggest some problem extensions. These will be additional AP Calculus type questions associated with the information given in the problem. And some of these extra problems may be calculator active. In this problem, we have a tank with a height of 10 feet, and the area of the horizontal cross-section of the tank at height h feet is given by a function capital A. The function A is continuous and decreases as h increases, and selected values for A of h are given in this table. In part A, we need to use a left Riemann sum and the data in the table to approximate the volume of the tank. And in part B, we need to determine whether this approximation is an overestimate or an underestimate for the volume of the tank. In part C, we're told that the area of the cross-section at height h feet can be modeled by this function f. And based on this model, we need to find the volume of the tank. Part D was perhaps the most challenging part of this problem, and here water is being pumped into the tank. When the height of the water is 5 feet, we're told that the height is increasing at a rate of 0.26 foot per minute. And using the model from part C, we need to find the rate at which the volume of the water is changing with respect to time when the height of the water is 5 feet. In this problem, there was a global units point, so a student was awarded 1 point for using the correct units in parts A, C, and D. Part A was worth 2 points, and to solve this problem, we used the general form of a left Riemann sum applied to the table and the given subintervals. Here we have 3 subintervals, and we take the height of each rectangle to be the value of A at the left-hand endpoint of each subinterval. Read the appropriate values of A from the table, and remember that final numerical answers do not need to be simplified. Part B was worth 1 point, and to answer this question, the student had to think about and visualize the rectangles in the left Riemann sum approximation. And because the function A is decreasing, the left Riemann sum approximation is an overestimate. Part C was worth 2 points. And to find the volume of the tank here, we simply need to evaluate a definite integral. Remember, however, that the student must present the mathematical expression first, here the definite integral, and then they can use their calculator to find the answer. Part D was worth 3 points. To solve this problem, we need to start with an expression for v of h. And then we take the derivative of v with respect to t, using the fundamental theorem of calculus and the chain rule. This is a nice problem. This is a calculator active problem, so the student can evaluate the function f at 5, and we're given that dh dt is equal to 0.26. Therefore, the volume of water is changing at a rate of 1.694 cubic feet per minute. In part A, it was pretty easy to find the left Riemann sum without a calculator. There were only 3 subintervals, and the products were pretty straightforward. However, here's a general calculator solution, which can be used for a larger table, and that also emphasizes, I think, conceptual understanding and notational fluency. Using the TI-Nspire, I first entered the values of h and a in a lists and spreadsheet page. On a calculator page, I first found n, the number of values in the list h. And here's a formula for the left Riemann sum. Note that the subintervals in this case were of unequal length, and this formula accounts for that generalization. Here's an extension of Part A. Let's suppose we have a slightly bigger tank, and this time with a height of 15 feet. The area of a cross-section at a height h is still given by the function a, and selected values of a of h are given in the table. Let's use a right Riemann sum with 5 subintervals indicated by the data in the table to approximate the volume of the tank, and then let's use a trapezoidal sum to approximate the volume of the tank. Here's the right Riemann sum, and be careful. Remember, we have to use the width of each subinterval. A common error is to assume that all subintervals have equal width. The right Riemann sum here, r sub 5, is equal to 71.4. And here's the trapezoidal sum. I think it's good practice to explicitly write out the area of each trapezoid. And here, t sub 5 is 130.05. Here's how I can use technology to answer these questions. Once again, I entered the values for h and a in a lists and spreadsheet page. Then, on a calculator page, I found the right Riemann sum and the trapezoidal sum. I think the use of technology here helps foster good use of mathematical notation. In Part B, we need to determine whether the approximation in A is an overestimate or an underestimate of the volume of the tank. Now conceptually we know that since A is decreasing, the left Riemann sum is an overestimate. But using technology we can visualize this idea. Since A is positive, it's a cross-sectional area, we can interpret the definite integral of A as the area under the curve. Now I cheated a little bit to construct this graph. I looked ahead to Part C, and I assumed that the model given there was a pretty good approximation for A. Note that the area of the shaded region here is 101. And it's pretty easy to see that the left Riemann sum is an overestimate for the area of this shaded region. Using this same model for A and the extended tank with height 15 feet, I used technology to visualize the right Riemann sum and the trapezoidal sum. It's pretty easy to see that the right Riemann sum is an underestimate. But what about the trapezoidal sum? Do you know for sure if this is an overestimate or an underestimate? What else would you need to know about the graph of the function a to answer this question? Part C is pretty easy to answer using technology. Here, I defined the function f, and then I simply evaluated the definite integral. The mathematical notation on the calculator screen sure makes this easy to read and encourages good written notational fluency. Here's a nice extended generalization of this problem involving Riemann sums. Once again, suppose the tank has height 10 feet, as in the original question. The area of a cross-section at height h is given by the function f. Consider the definite integral of f from 0 to 10, which represents the volume of the tank. First, use technology to complete the table. These are values of the left, right, and midpoint sums for various values of n. Once this table is complete, here are some questions that involve the results and the patterns in this table. First, how do your results change in relation to the exact volume as n increases? No matter what value of n we use, the left Riemann sum always returns an overestimate in this case, and the right Riemann sum an underestimate. Explain this result. What characteristic of the function f can be used to justify this answer? As you examine the results in this table, the midpoint sum always seems to return a better estimate of the exact volume, as opposed to the left or the right Riemann sum. So why is it that the midpoint sum is always closer to the exact answer for fixed values of n? After completing this table, and perhaps visualizing some of these Riemann sums, can you suggest a better way to estimate the area under this curve, or equivalently the volume of this tank, based on different geometric figures, different than rectangles? And explain why this method would produce a more accurate estimate of the area. There is a nice math-inspired activity and TNS file on the Texas Instruments website that can be used to answer these questions and visualize results. Here are two screenshots from the Riemann Sum Activity TNS file. There are sliders to adjust the value of n and the type of sum, and the approximation is given along with the exact value, and all of the appropriate rectangles or trapezoids are drawn to help visualize the sum. I hope this video gives you some good ideas for additional practice AP Calculus type exam questions, and of how to use technology to solve some of the parts of this problem, and to explore, confirm, and visualize results. And just a reminder, there are lots of valuable resources on the TI website. There's material there involving technology and calculus, classroom activities, and lots of calculator tips and tricks for test success.